Okay, so P1 is 2, P2 is 3, and so forth. Okay, so we can look at prime gaps, which is just the difference between one prime and the next. Okay, given one prime Pn, how long do you have to advance before you see the next prime? Okay, so the first prime gap is 1. After that, they're all even numbers because all primes are odd after 2. So the prime gap starts at 1, and then you have 2, 2, 4, and so forth. And so you have this sequence of even numbers. And you can ask two basic questions about this prime gap. Okay, so one is how small can this prime gap be in terms of n for large n, and how large? Okay, so it's almost the most basic questions you can ask. Okay, and in both of these questions, we have a conjecture, which looks impossible to solve by our current methods, but we also have progress. And in both cases, actually, we have progress in the last 2 years. We have this nice symmetry, actually. And ultimately, as it turns out, we actually use the same method to attack both questions, which was not obvious, actually, when we started this. Okay, so I'll start with the first question. Okay, so the basic conjecture here is one that most of you probably know, is the twin prime conjecture. That there are infinitely many prime twins, infinitely many pairs of primes that are distance 2 apart. So another way of saying that is that the prime gap is equal to 2 infinitely often. Okay. As the primes, as you go out into the primes, we know the primes do get sparser and sparser. So on the average, the prime gap actually increases, roughly like the logarithm of the primes, actually. But we still expect every so often, just by pure chance, basically, the prime gap should every now and then return back to be as small as it can be, which is 2. Remember, it has to be even. Okay, so this is still open. This was first explicitly posed by de Polignac in 1860 something, and it's still open. For a long time, it was basically just seen as completely out of reach. But we had this amazing breakthrough by Yitang Zhang last year. And the precise date is actually May 14th, 2013, who for the first time managed to get a bound which looks like this. What he showed was that the prime gap is bounded infinitely often. And the bound, he even got an explicit bound, pretty large, but explicit. Okay, that there are infinitely many pairs of adjacent primes whose distance between each other is not 2, well, it could be 2, but it is certainly bounded by some large but fixed constant. So this is the first bound of this type. So previously, the best bound like this, just for comparison, one could get a bound which is basically a square root of the logarithm infinitely often. This is what's our Goldstone-Penzignoli theorem. About 10 years ago. Okay, but this was the first actual bound. So this was an amazing result. It's now published in the Annals of Mathematics. It's amazing for several reasons, partly because of Yitang's life story. He was an assistant professor in the University of New Hampshire, who actually hadn't published for a while and even left academia for a while, but still was working on this problem and actually solved it and wrote completely correct proof. So there's nothing too special about this number 70 million. It's what came out of Yitang's argument, and he wasn't completely careful. His goal was not to get the sharpest possible number, just to get sort of a nice round number, which was large enough for everything that he wanted to do. And so very quickly after his preprint was made available, people started noticing, oh, if I optimize this line, I can change 70 million down to 63 million. And somebody else said, oh, I can actually shave it down to 58 million by this extra trick. And so just so spontaneously, people started going through the papers and finding, very, very briefly holding the world record for the bounded gaps, the bounded gaps between primes. And so eventually, myself and several other people organized this into an online project, which we call a polymath project. It's a play on words. polymath means someone who is good at many things, but here we mean it to mean many mathematicians, polymathematician, working together, each sort of focusing on one aspect of Zhang's argument, and some doing some numerics, and other people adding some theoretical advances. And so we worked online for several months, and we managed to improve this bound, I think, by July 27th. We managed to get the bound down to about 4,000, and then at which point we began to get stuck, and we started writing up the results. So, okay, we were all very happy with that. But actually, before we had finished writing up, actually, it turns out it was almost 160 pages worth of stuff, actually, calculations that we had to actually write up. It's just been trimmed down a bit. But before we finished, actually, we found, we were surprised that independently of our work, but probably inspired by what Yitang did, a postdoc at Montreal, his name is James Maynard, and the time here was November 19th, found a shortcut that cut out a lot of the difficulty in Zhang's argument. Zhang used quite a bit of firepower. Just to give you one example, there's a very famous result of Deligne proving the Riemann hypothesis over finite fields, and it won him the Fields Medal and the Apple Prize and so forth. And Zhang used that to get this, and we also did as well. But Maynard found a shortcut that cut around a lot of this, and so he managed to find a much shorter argument, which of the same, okay, but he got a much better bound of 600 actually. Okay, so after that came out, so my group got very excited, and we started talking to Maynard, and so he decided to join forces with us, and so we worked a little bit more to combine our two methods, and so we worked on that for quite a while, and we eventually got, so that the final thing that we declared victory at was back in April. Okay, so our bound is now 246, and it's possible with lots of computer power to maybe shave another 4 or 6 out of this, but it got really complicated, and we thought this was a good place to stop. Now, this was for the purposes of an online project, it was really good to have this number as sort of a score, right? Because it was a very tangible measure of progress, which is something that you don't often get in a mathematics project. I should say though that there's nothing that special about these numbers. What's more interesting ultimately is the techniques that go to proving these things and the various advances in technology that you need to get from one to the next. But still, it's nice to have this very clean progression here. But unfortunately, this looks like it's approaching 2, but slowly. But unfortunately, we do know that these methods cannot attain the twin prime conjecture. So what we can prove now is that if you assume, all these results are proven using the methods of sieve theory, which I'll talk about later. And there's a certain conjecture in sieve theory which is kind of like the Riemann hypothesis. There's something called the Elliott-Halberstam conjecture. I'll explain what it is a little bit later, well, roughly. But it's sort of like a generalized Riemann hypothesis for sieve theorists. And if it is true, we can improve this bound all the way to 6. That we can get infinitely many pairs of primes 6 apart. So pairs of primes that are 2 apart are called twin primes. Pairs of primes that are 4 apart are called cousin primes. And pairs of primes that are 6 apart are called sexy primes. So this would mean that there's either infinitely many twin primes, infinitely many cousin primes, or infinitely many sexy primes. This is a cute way of phrasing it. But unfortunately, we know also that this is the limit of the method, that there is no purely sieve theoretic method that can lower 6 to anything smaller. So if you want to actually get all the way to 2, you have to use something different from anything that we do here. Okay, so these are some of the results we have. We have other results as well. So one way to think about these results, for example, this result here is saying that you can find infinitely many intervals of length 600, which contain 2 primes. It turns out that some of the later methods, starting with Maynard and going forward, can also find intervals which contain many primes. So not just which means. So rather than talk about prime gaps, you can also talk about P n plus 2 minus Pn, and there's some bound for this, and there's a bound for Pn plus 3 minus Pn. You can find intervals of bounded length that contain 3 primes, 4 primes, and so forth. And this will become somewhat relevant later on. But there are other variants of this. And so the methods that have been used to prove this, these prime gaps results have also been used to prove many other things in number theory. There's actually now, this is only like 12 months ago, but there's already like a dozen papers using variants of what we now call the Maynard sieve, or Maynard Tau sieve by some people, okay, to prove other things. Okay, so this is the state of the art for small prime gaps. Now let me briefly talk about large prime gaps. Okay, so a large prime gap is the same thing as a big long string of composite numbers. Okay, if you have a whole bunch of composite numbers, then the prime before and the first prime to the left of that string and the first prime to the right of that string has got a big gap. So one of the first things you can prove, and this is something that you sometimes you can see in high school, is that the prime gap can be infinitely large. So this gap can be arbitrarily large, and there's a very simple proof. Given any number n, you take its factorial, and you look at this consecutive string of numbers. All the numbers from n factorial plus 2 up to n factorial plus n. Let's say n is at least 2. Okay? And these are all composite numbers, because this guy is a multiple of 2, which is bigger than 2, so it's composite. This guy's a multiple of 3, which is bigger than 3, so it's composite, and so forth. So you've got this whole string of composite numbers of length n minus 1. So that means that the primes to the left and the right of this string must have a gap of at least n minus 1, maybe even n. And n can be as big as you want. So the prime gaps can be as big as you want. Now, we can do better than that by using some slightly more advanced technology. So one of the first basic theorems that we can prove about the primes, maybe the most important theorem about the primes, really, is the prime number theorem, proven in 1890-something. I should know this. Okay, but I think 1896 or 1897. Okay, so the prime number theorem tells you roughly how many primes there are up to any given level. So it tells you that the number of primes up to a large number x is roughly x1 log x. And this is the natural log of x. Okay, and roughly what you mean is that you actually have to multiply by a little error which goes to 0 in relative sense. So the ratio between the number of primes up to x and x over log x goes to 1 as x goes to infinity. Okay, so for a large number x like a trillion, the number of primes up to a trillion is roughly a trillion over natural log of a trillion. So that's how many primes there are in this interval. And so just from the pigeonhole principle, okay, what this tells you is that among the primes, among the primes up to x, there is at least one prime gap minus Pn, which is bigger than log x. Maybe it's a little error. Okay, or another way of saying that is an equivalent way, is that the prime gap can be as big as small factor times log Pn. The prime gap can be as big as the logarithm of the prime, of say the first prime, infinitely often. Okay, so this is an easy consequence of the prime number theorem and the pigeonhole principle. Okay, so can you do any better? Okay, can you make the prime can the prime gaps be any bigger than this? So we don't actually know so much about how big the prime gap can be. I think the best unconditional bound we know is that the prime gaps are always at most a constant times Pn to the, I think, 0.55. This is, so they can't be incredibly huge, they can't be bigger than 0.5, basically almost the square root of Pn. This is a theorem, I think, of Heusill. No, Baker, Harman, and Pintz, this one. Okay, but if you assume the Riemann hypothesis, you can get a slight improvement. We know that you can improve this to Pn to the 1/2, I think, times log Pn.
So what's the first one?
0.55, yes. It's just a numerical constant coming from optimizing all kinds of other things. If you assume the Riemann hypothesis, we can bound the prime gap up to the square root of Pn, basically. But that's still quite far from this pigeonhole. And And this is not expected to be the truth, but this is just the best we can do, even assuming this very heavy machinery here, which is the Riemann hypothesis. So the conjecture that everyone believes is due to Cramer. So he introduced a random model of the primes. So he modeled the primes. So the primes up to x are just some set of numbers up to x, okay? And we know how many numbers there are. But of course, knowing the number, the cardinality of a set doesn't tell you everything about the set. It doesn't tell you its distribution. So Cramer had the idea, well, let's pretend that this set we know is cardinality. Let's pretend that it looks random. So he modeled the primes by a random subset of numbers up to x of the same cardinality, of cardinality approximately x over log x. So in a way, it's sort of giving up on the question of what patterns there are in the primes. Let's say, I don't understand the set of primes, let's just believe it is a random set. Of course, the primes themselves are not actually random. You don't have to roll any die or flip any coins to create the prime numbers. But the modern way of thinking of Cramer's model is to say that the primes behave pseudo-randomly, that they behave like a random set, even though they're not exactly random. Now, the reason you want to do this is because we have this probability theories are very good at computing what happens to random sets. And we can compute all kinds of statistics of random sets. So for example, if you take a random set of numbers up to x of this cardinality, you will find a lot of twins, a lot of pairs of numbers 2 apart, quite a lot actually. And so this gives you some evidence, some heuristic evidence that twin prime conjecture is true. If you take this random subset and you look at gaps between now these sort of fake primes, these sort of random model of the primes, what you find is that the prime gaps are now this random variable. They'll be distributed like a Poisson random variable whose, sorry, an exponential random variable. Yeah, the set looks like a Poisson process, but the gaps have this exponential variable of mean log x. And so you can get gaps larger than log x, but they get exponentially rarer as you make the gap bigger and bigger. And by computing the random model, Cramer conjectured that the correct size of the gap should be log Pn squared. Okay, that if you make a sufficiently, for a small constant c, for a sufficiently small c, okay, that if you make this constant c small enough, you should have gaps that are as large as the square of the logarithm infinitely often. But then he also conjectured that if you make the constant big, this should only happen finitely often. Actually, maybe he didn't quite conjecture that, but this is what the same model would predict for you. Okay, that the largest gap should be roughly of the order of log squared. Okay, you should get an extra log over what the basic equational principle gives you. Okay, but this conjecture looks really far from reach. So I mean, the twin prime conjecture, I can believe that we just one or two clever ideas away from actually solving this. I mean, we know sieve theory by itself can't do it, but maybe we just need one or two more clever ideas, and we could maybe do this conjecture. This, I don't think we're anywhere close to solving. One of the reasons is that twin primes are still fairly numerous. At least we believe them to be fairly numerous among all the primes. So as I said, the number of primes up to x is about x over log x. The random heuristics that come from this Cramer model suggest the number of twin primes up to x is about x over log squared x. Which is still quite a large number. There's a lot of twin primes, and you just need to find one twin prime in every, say, interval between x and 2x for large x. It doesn't look completely impossible. But with this, with the large prime gaps, the larger you make your gap, the fewer and fewer prime gaps you have with that large gap. Well, at least that's what we believe, and the density decreases exponentially. So, for example, there should only be like one prime gap this huge in any interval between x and 2x, or something like that. And so these are very hard to find, these huge gaps. So I don't think we're anywhere near as close to this conjecture as we are to the twin prime conjecture. Although this one is also, we are still quite far from that too, unfortunately. But we have some progress. Okay, so it turns out between log x and log squared x, it turns out to be a surprising amount of intermediate room, at least to a number theorist. So there's a sequence of results, and it's pretty, well, the list is somewhat amusing. So the first non-trivial result was by, I can't pronounce the name, Polish mathematician, West Xinthius. In 1931, who managed to beat the Bigelow principle. He was the first person to beat the Bigelow principle. And he showed that you can get prime gaps that are as large as log Pn times a correction term, and his correction term turned out to be log Pn. Except he couldn't quite get that, so he had to divide by log Pn. Okay. There is a joke, not a very good joke, but yeah, what did the drowning number theorists say? And the joke answer is log. But anyway, okay, so he was the first to get some non-trivial improvement. This was quickly improved, or not so quickly, but by Erdős in 1935. I think this is true infinitely often, of course. Okay, and the same result, but now slightly less embarrassing logs. Okay, just 2 logs on the top and 3 logs on the bottom squared. Okay, and then Rankine in 1938 managed to improve this just a little bit more. He could get prime gaps as large as a constant times log Pn. Okay, again, 2 logs over 3 logs squared, same bound. Okay, and then he was able to add an extra 4th log up here. Okay, and C was, I think, 1/3 in his first paper. Okay, so so there was some progress here, but amazingly, what happened afterwards was that this people got stuck at this bound for over 70 years. So over the next few decades, people were able to improve C a little bit, but they could not get past this funny natural expression of a combination of logs. So C started steadily improving. There were results of Schonhager and then Rankine again, Mayer and Pomerantz, and then finally Pintz until this year. The most recent result on this was this the same result, just C was a bit bigger. C was actually 2 times e to Euler's constant, which is a number to about 3.56 something. Okay, but other than that, there was no further, there was no gain to this. In fact, this was so stubborn and so mysterious that Erdős, who was fond of giving out cash prizes for various problems, actually offered $5,000 to anyone who could actually improve, to show that this constant could be taken arbitrarily large, which is the same thing as basically adding some extra log or something to this expression here. So this is where things were stuck at for some time. But then there was a breakthrough this year. And the funny thing about this subject sometimes is that sometimes the time is just right for a breakthrough. So Maynard, for example, was working independently of Zhang on prime gaps, and the people were stuck for 10 years. And then there were these 2 results which are pretty much independent of each other. Maynard was already working on this problem before Zhang. And so we now have these 2 new methods of proving bounded gaps. And the same thing happened here with large gaps. So, so very recently there was a result of Kevin Ford, Ben Green, Sergei Konyagin, and myself. And this was 20th of August. Okay, so what we proved is that you can take C arbitrarily large. Okay, so this is true. Okay, that you can get a tiny improvement over this. And amazingly, the next day, this has happened to me before. Though not actually. Once it actually has happened 24 hours apart. But sometimes I think just the ideas are in the air. So James Maynard released a proof the next day, proving the same result by a different method. And yeah, so it was truly independent. And actually, the amusing thing is actually used with results that were used to prove small prime gaps to also to prove large prime gaps, which is a nice symmetry. So since then, we've joined forces, and we can now actually push this a little bit further. So as of, I think, last week, we can, all together, well, if you put everything together, what we can do is that we can get rid of one of the logs on the bottom. Okay. Yeah, so you can see we're not really getting all that close to Cramer's conjecture of log squared. These are still quite small improvements. And there is a serious limitation to our methods. We're not going to get anywhere close to Cramer. This actually, we believe, is the limit, the new limit of our methods. You will need a new idea to get beyond this particular thing. So, you know, but still, it is nice progress, and it uses some of the theory we had before.
What year were these two?
This year.
That's this year.
Yeah.
Fresh.
Yes. Ben actually announced it at the ICM in Korea. Okay. Okay, so these are the results. So let's talk about some of how we prove things. So let's go back to small gaps. Okay, so so we have the Pigeonhole principle gives you something. Okay, so the same Pigeonhole argument that gives you large prime gaps also gives you small prime gaps. So again, the prime number theorem is that for any large x, the number of primes less than x, or let's say between x and 2x. Okay, if you take an interval between x and 2x, the number of primes in this interval is basically x on log x. And so again, from the Pigeonhole principle, this tells you that there exists a prime gap in the interval between x and 2x of length, of order log x or less. Okay, so just from counting, because the sum of all the gaps adds up to x, and there's about x over log x of them. So just from the Pigeonhole principle, there has to be one gap which is less than or equal to the average spacing. Okay, but we want to do better than this. We want a bounded prime gap, not a gap that goes logarithmically. So all right, so how can you proceed? Well, I can rewrite this argument. So this is a very simple argument, this Pigeonhole argument, but I can rephrase it in probabilistic terms. So probabilistic reformulation. Okay, so what I'm going to do is that I'm just going to find a prime. I will look for a prime randomly. So what I will do is that I will pick n, pick a natural number n uniformly at random. Between x and 2x. Okay, so just pick some number uniformly at random from x to 2x. So it's a random number. It may be prime, it may not be prime. It will probably not be prime, but there is some chance that it is prime. You can compute the probability that you're prime. And from the prime number theorem, there are about x numbers between x and 2x. If x over log x of them is prime, the probability that n is prime is roughly about 1 on log x. Okay, so if you pick a number at random, you've got about a 1 log x chance of it being prime. Okay, that's not very big, but it's something. Okay. Similarly, if you look at the probability that n plus 1 is prime, if you take a random number between x and 2x and you add 1 to it, that's basically another random number between x and 2x. Not quite, but essentially it is. And so again, the prime number theorem also tells you that the probability that this is prime is also about 1 in log x, and so on and so forth. Okay, so you can start. You can take. You can shift your random number by various shifts, 0, 1, 2, up to some shift, say capital H. And H is going to be of size about log x. Okay. Okay, so you can take your random number and shift it H times, and each time you shift it, you've got another event that this shifted number might be prime, and there's some probability about 1 in log x that this is prime. Now, if you pick H to be of size just a little bit bigger than log x, you can make all these probabilities sum to be bigger than 1. So if you add up all these probabilities, individually they're small, but if you keep adding them together, they eventually get big. So for H about this size, you can make the total sum of this guy. Okay, you can make the total probability of all these events exceed 1 once you make capital H big enough, and about log x. Okay, and the moment you do that, the probabilistic Bigelow principle tells you that if you have any set of events and the total probability adds up to more than 1, then somewhere with positive probability, 2 of these events happen together. Okay, they can't be disjoint. So somewhere, for some n, there must be 2 shifts, n plus h1 and n plus h2, where h1 and h2 are of this size, where they're both prime. And that gives you a prime gap of size less than log x. Okay, so this is a very complicated sounding reformulation of the Bigelow principle argument. But this is a good reformulation. And the reason that it's good is because it generalizes. Okay, so this argument is very slick, but it's sort of hard to see how to generalize it. This argument, okay, so first of all, rather than taking consecutive shifts, you could be maybe slightly cleverer and take targeted shifts. Maybe shift h1, h2. You can shift your random number by some well-chosen shifts, and as long as you can make the total, okay, and this probability is equal to something, this probability is something else. As long as you can make the total probability of these guys being prime add up to more than 1, you can, and if these h's are not too far apart from each other, you can create a fairly small prime gap from this. So you can try to play with different h's. Although if you pick n uniformly at random, it turns out no matter how you shift, you always get 1 over log x, and so you can't do much better than this log x bound that I already said. But the more relevant thing, once you phrase things this way, is that once you phrase things probabilistically, you begin to see that there's really no reason that you have to pick n uniformly. That maybe if you pick n not uniformly at random, by some other well-chosen probability distribution, maybe you could pick a better distribution from numbers between x and 2x, such that you've got a better chance of making these guys prime, and so that you can increase each individual probability, and then maybe you need fewer of these terms to sum to be bigger than 1, and maybe much less than log x. Okay, so for example, if you want n and n plus 2 and n plus 4 to be prime and so forth, picking n uniformly at random and hoping that you get a prime is kind of silly. You should, at the bare minimum, only search the odd numbers if you want n or n plus 2 or n plus 4 to be prime. Okay, that already doubles basically all the probabilities here. Okay, so that already gives you a win. The price you pay though is that the h's have to become further apart. You can't take consecutive numbers; you have to take consecutive even numbers. But that already gives you some idea that you can play some games here. That rather than work over a uniform distribution, maybe work over a uniform odd number, or maybe a uniform odd number which is also coprime to 3, or something like that. And so you can start. Okay, so phrasing things in a non-probabilistic manner. Basically, you have a freedom to choose a probability distribution now. So now the new goal is to find a probability distribution, or equivalently, basically a series of weights, a sequence of positive numbers for n between x and 2x, such that if you so use these weights to create a probability distribution by normalizing by the sum. Okay, so you sum all these up, you get some number, and then you sum up all the n's for which, say, n plus h1 is prime. Okay, so this ratio, the probabilistic interpretation of this ratio is that this is the probability that if you choose n using this weighted, this particular set of weights as a distribution, that you get a prime when you shift by h1, and then you shift by. So if you shift, you do all these shifts, and if you can add up all these shifts, and you can get this thing bigger than 1, this implies that for some n, at least 2 of the n plus hi prime. Okay, and if the h's, if the hi's, if the shifts are fairly close together, you can get a fairly narrow prime gap in this manner. Also, if you can make this ratio so big that it's bigger than 2, then not only can you get 2 of these guys prime, you can then get 3 of these guys prime, and so on and so forth. So that sort of brings us to some other things I mentioned before. Okay, so basically all you need to do is that you need to find a clever choice of weight, which on the one hand, you want the total sum of the total mass should not be too big. You want this denominator to be small, but you want these numerators to be big. You want so you want to find basically what's called a sieve, which catches a lot of primes. That relative to its total size, the portion of the sum coming from primes is relatively big, much bigger than 1 over log x. Okay, so one just has to pick this weight properly. So the game then is to find a very clever choice of weight which does this. So, so you could try the uniform weight, but that doesn't work very well. You could be overly clever, and for example, if you wanted to maximize the probability that say n is prime and n plus 2 is prime, you could pick n not to be uniformly random. You could pick n to be uniformly random among the twin primes from x to 2x. So from x to 2x, you pick all the twin primes, and then of course you're guaranteed if you do that, you're guaranteed that the probability that n is prime is 1, probably n plus 2 is prime is 1, 1 plus 1 is bigger than 1, and you win. Now, why doesn't that solve the problem? The problem is that that corresponds to selecting nu of n to be 1 when n is a twin prime and 0 otherwise. And there the problem is that you can't prove the denominator is non-zero, unless that's a hard resolution problem. So if you want to make both of these probabilities exactly 1, we can't do that. But we don't need to get anywhere near that far. Okay, you could if for example you could find a weight where the probability n is prime is at least 0.6 and n plus 2 is at least 0.6, that's already good enough. And so you can hope to find smarter choices of this weight, which you can actually compute these sums without having to resort to unproven conjectures, and then hopefully you can make these numbers big enough that they sum to bigger than 1, and then you can declare victory. So this is ultimately what everyone did. So this strategy was introduced by Goldson, Pintz, and Yildirim about 10 years ago. And that's how they got their first partial results on prime gaps. Now, it turns out nowadays, that, so the question is what weights do you pick? And so on the one hand, you want the weights to always be positive, because otherwise you don't get a probability distribution. On the other hand, you want the weights have to be simple enough that you can actually compute these sums. And it turned out, after a lot of trial and error, that the correct choice of weights, so that the best choice of weights that we have currently, come from what's called the Selberg sieve, introduced by Atle Selberg in the 70s, I think. And so his weights, so if you want n plus h1 and n plus, if you want to make a sieve such that all these guys have a high chance of being prime, the Selberg sieve, what you do is that you take all these numbers that you want to be prime, and you multiply them all together, and you get one big number. And you look at all the divisors of this big number, and then you take some sum. You take some sum of this you sum some coefficients based on the sum, and these are positive or negative coefficients. And you take the sum and then you square it. Okay, but you don't take all factors. You take all factors up to a certain level. So there's some parameter r that you pick. So you take all the factors of this big number up to some level r. You choose some weights, and so you get to pick what weights you have here, and then you square this. Okay. So the reason you square this is to guarantee that it's positive. So these guys can be negative, but the square is always non-negative. So this is always non-negative, and this turns out to be a fairly tractable expression to compute. For example, if you want to compute u of n, okay, if you unpack this, this is equal to, if you square this out, this is equal to like the sum of all pairs d1, d2 up to r, then there's some weights, another weight, and then you're summing all the numbers n between x and 2x, one subject to the constraint that d1 and d2 both divide n plus h1, n plus h2. So this is just expanding things out. Okay, and the point is that this is something which is actually fairly easy to compute. So if you're just summing all the numbers from x to 2x, this is basically just x. Here you are summing all the numbers n such that this product is divisible by d1 and d2. So in other words, it's divisible by the least common multiple of d1 and d2. Now, if d1 and d2 are bounded by r, this number is bounded by r squared. So as long as you pick r small enough, like r less than, say, root x, if you pick r small enough, the modulus here is less than x. And so this constraint is a periodic constraint whose period is less than the interval in length of the interval here that you're summing over. And that turns out to make this sum very easy to compute. And then what you get is you get some quadratic form in these coefficients. Okay, so and quadratic forms are something that we don't scare us too much. If you, instead of summing all of these guys, you're summing, for example, this sum weighted by the fact that this guy is prime, then you get a very similar. You get a very similar sum over here, but rather than summing one, you're summing primes, the indicator function of the primes. And so what this sum is basically, roughly speaking, this is counting how many primes there are in an arithmetic progression. Okay? And there are lots and lots of theorems about what primes do in arithmetic progressions that you can use from analytic number theory. So the number theoretic input is then, to control this, you use facts about the number of primes in arithmetic progressions. So you may know, for example, Dirichlet's theorem that if you have any residue class A mod Q, where A is coprime to Q, that this residue class always contains infinite many primes. So that fact by itself is too weak to actually say much here, but there are stronger versions of Dirichlet's theorem that can go into here. For example, if you know GRH, you can plonk it in here. But even without GRH, there are various ways you can compute this expression, and so you get another quadratic form. So this funny ratio here, what it is with the Solberg sieve, becomes a ratio of two quadratic forms with coefficients that you can pick. And we know how to optimize quadratic forms. Right? Then you can do some linear algebra, and you can start doing this. And so it turns out that if you run this machine using the best theorems about primes and arithmetic progressions that were already available before Yitang Zhang's work, you just barely fail. You can get this ratio as close to 1 as you wish, but you can't quite make it equal to 1, which is very annoying. So Goldstine, Newton were not able, using this method, so they introduced this method. They were not able to get bounded prime gaps, but they got really, really close. And the problem was that they didn't have a strong enough theorem about primes in arithmetic progressions. And Zhang's big breakthrough was that he found a new theorem about primes in arithmetic progressions that was not available before. Okay, maybe I won't actually say exactly what it is. But if you want to count the number of primes up to x in an arithmetic progression, like A mod Q, this turns out to be a fairly easy task if Q is small, but when Q gets bigger and bigger, the progression is sparser and sparser. It's harder and harder to count the primes. And the standard tool in sieve theory is something called the Bombray-Vinogradov theorem, which allows you to count primes in arithmetic progressions as long as the space in Q is not too big. Basically, as long as Q is less than x to 1/2. As long as you don't make the spacing any bigger than square root of x, we have a very good theorem that tells you what the primes do in most of these arithmetic progressions. And what Zhang did was to be able to stretch this theorem a little bit and also say just a little bit about primes in arithmetic progressions which were spacing just a little bit bigger than x to 1/2. But it was a tiny amount. I think the amount he got was like 1/568 or something. But that was just enough to tip the balance to make this expression just barely bigger than 1 if k was big enough. I think k had to be something like 3 million. And this is how he got his 70 million bound initially. And then subsequently we were able to push this, enlarge this constant further and optimize other parts of the argument. Okay, so and Zhang worked quite hard to get that tiny, this little epsilon. Actually, he'd use a lot of Fourier analysis, a lot of this work of Deligne on exponential sums, and an incredible number of applications of the Cauchy-Schwarz inequality. Anyway, he was able to get that. So Maynard later on found that you didn't actually need. So he spent a lot of effort to get this improvement. But actually, even without that improvement, using just the existing prime number theorems in arithmetic progressions, Maynard was able to get the same sort of result. And so his observation was actually very simple, which is that this was not the only sieve you could pick. So the standard sieve until then had been to multiply all the numbers together here and take the divisors of this product and create a sieve. But then Maynard, and actually I realized this independently at the same time. That's another instance where actually of simultaneous discovery. But what he realized is that there's a more general sieve you can pick here. So rather than look at the factors of the single product, you can just sum over the separate factors, which in retrospect is a very simple idea, and we should have realized this earlier. In fact, it had been realized earlier, this idea. But the reason why it was not studied further, I think, was unfortunately the first paper to analyze this sieve actually had a serious error in it. And so it was somehow discredited, and people didn't pay attention to it until 10 years later. So rather than look at the factors of this big product, you split up the factors into k pieces. So now you have this multi-dimensional sort of weights here. But then you can actually turn out you can run the same game, and you have another quadratic optimization problem, and now in many dimensions rather than one dimension. It turns out that it reduces to a certain calculus variations problem, that you have some multi-dimensional integral of a certain test function, quadratic form of a test function, and in both the numerator and denominator, and you want to maximize the ratio. And it turns out that if you choose the right test function, you can actually make this ratio much bigger than in the one-dimensional sieves. And this is how he was able to get his results, where in fact he could make this ratio as big as he wanted. You can get many primes in a bounded interval, not just one prime. Okay, and then afterwards, the Polymath project improved this further. We got some experts in quadratic optimization on board, and they started optimizing these huge matrices. And this is how we got our bound down a little bit further. And we made some other improvements too. Okay, so that's all I want to say about small prime gaps. So let me talk now about large prime gaps. So as I said before, there is a simple construction of large prime gaps. So finding large prime gaps is basically the same thing as finding large consecutive strings of composite numbers. Okay? And the simple construction is just to take n factorial, and then you shift it by the numbers from 2 through to n. And this already gives you a large prime gap. If you fool around with Stirling's formula, this construction does give you a prime gap. And it tells you that the gap here is about log Pn over log Pn, infinitely often. This is what comes out of Stirling's formula. So that's not so great. This is actually worse than what you get from the prime number theorem. Prime number theorem, the Pidgeon principle already gives you log Pn, and you're actually one log behind if you use this simple construction. Okay, but you can be a bit smarter than this. N factorial is a bit wasteful. There's a smaller version of n factorial called n prime. This is called the primorial. The primorial of so the factorial of n is all the product of all the numbers up to n, natural numbers. The primorial of n is the product of all the primes up to n. So you only multiply the prime numbers, forget the composite numbers. And the same construction you take the primorial of n and you add 2 to it, add 3 to it, all the way up to add n to it. You still get all these numbers are composite, exactly the same argument. And this primorial is a bit smaller. So n factorial is a bit like n to the n. This is more like exponential of n. And so if you use the primorial, which is the smarter thing to do, you can recover the Pidgeon principal bound. Okay, so you're at least not losing anything, but you haven't gained anything yet either.
Are the shifts in the naturals or just the primes using the primorial?
Sorry, what?
The shifts in the
Oh yeah, you use all the numbers here. So
all the numbers.
Yeah, you need a consecutive string of composite numbers to get a large prime gap. If you even miss one, then you, yeah. Yeah. Okay. So, so why did this work? Okay, so you can generalize this. So another way to think about this construction is that what we're doing is that if you look at this interval, this block of consecutive numbers from 2 to n, you can cover this interval by residue classes. That if you take the multiples of 2, okay, so that crosses out some of these numbers. You take the multiples of 3, so this is basically the Sifert Eratosthenes. And if you take the multiples of all the primes up to n, every each of these residue classes, between them, they cover this interval. This interval is completely sieved out. It's completely covered by these residue classes. Every number from 2 to n is divisible by 1 prime at least between 2 and n. And it's because of that's what makes this, this whole string consist entirely of composite numbers. Because everybody here is divisible by some prime. You shift it by the primorial, which is divisible by all the primes up to n. And so everybody here is divisible by 1 prime up to n. Now, if you phrase things this way, what you realize is that more generally, if there's any interval, you take any interval, and if you can cover this interval, maybe not by the zero residue classes, but if you can find some congruence class mod 2, maybe not call it A, I don't know, let's call it C, some congruence class mod 3, and so forth. If you can find some congruence class mod 2, mod 3, mod 5, which together cover every single interval here, then you can shift it by n factorial, maybe not by n factorial, but by some other number. Okay, you can use the Chinese remainder theorem to find some number y, which is, I think, has to be minus C2 mod 2, minus C3 mod 3, and so forth. If you can find, so by the Chinese remainder theorem, because these are all different primes, you can find some number between 1 and the primorial, which mod p is minus Cp. And then if you shift this interval by that y, what you'll find is that every number in here is divisible by one of the primes up to n, and you would still get a string of consecutive numbers. So really what's going on in this construction is the fact, it's the fact that this interval between 2 to n can be covered by residue classes of primes up to n. And so if you can find a longer interval which can also be covered by primes up to n, then you can start beating this result. Okay, so now the question becomes another sieve theoretic question. What is the most efficient way, if you have a long interval of numbers, what's the most efficient way to take a residue class mod 2 and mod 3, and so you're allowed to translate each one, okay, but you want to slide them around in such a way that they cover everything. Okay, so this becomes more of a combinatorial problem. So it turns out that if you use all the primes up to n, so the way we prove our theorems is that, so using the primes up to n, we can cover all the numbers from 2 to n. But actually now we can cover all the numbers we can cover a slightly longer interval. So I think the record currently, all right, well, it's not so important exactly what it is, but we can cover an interval slightly larger than n using only primes up to n. And so how do you do this? The way you proceed here is that you sort of you modify the Sifert Eratosthenes. You use the zero congruence class for most primes, say all primes up to say n over 2. Okay, if you sieve out all the multiples of all the primes up to n over 2, that already cuts out a lot of numbers. Any number that has any prime factor less than n over 2 will be killed. The only thing that survives, well, first of all, 1 will survive. That's not very interesting. But basically, the only survivors, so the survivors are mostly just the primes. Between, I think, n over 2 and this big number, let's call y. Okay, so the primes are basically the only numbers that don't have small prime factors. Okay, So if you sieve out all these numbers, all that's left are the primes, and we still have all the primes, but we still have some primes left over. We still have some residue classes between n over 2 and n to play with to sort of kill off any further survivors. As it turns out, strictly speaking, we don't quite do this. We sieve out this for most primes p, and then we randomize it. Some of the primes, it's actually better to pick random residue classes rather than zero. So there's some optimization here which I will gloss over. But roughly speaking, using some of these residue classes, you can reduce to just primes in here. And then the question then becomes, can you cover the remaining surviving set of primes efficiently by congruence classes coming from these primes here? And so what the problem boils down to is, can you, for a given prime p between, say, n over 2 and n, can you cover the primes? Okay, can you find a congruence class, Cp mod p, which catches a lot of primes? A lot of primes in this interval from 0 to 1. Okay? But heuristically, if for every prime or most primes p in this range, if for each prime p you can find some congruence class each of which captures, say, hits about 10 primes from 1 to y, then if there are like n over log n primes here, then between them, all these primes should be able to hit maybe 10 n log n primes. So you should, and so the more primes that you can hit with each congruence class, the more efficient you can make the sieving process. So this becomes the basic question. So when Ben Green, Kevin Ford, Sergey Konyagin, and I got interested in this, so this looked very similar to something that we had worked on 10 years ago, Ben Green and I. So 10 years ago, we had studied arithmetic progressions in the primes. And when in particular, we were able to find nice long arithmetic progressions of any length you wanted, where everybody is prime. Okay, so, or in other words, we could find a congruence class mod R, which hit a lot of primes. Now, in our first paper, this R was just a number; it wasn't prime. We had a subsequent paper in which you could basically force R to be basically a prime or maybe a small multiple of a prime. So we used our machinery from several years ago on counting things like progressions and primes to be able to answer this question. But it was quite complicated because these results were themselves rather non-trivial. But what James Maynard did, he seems to have a knack for always finding the simplest way to solve a problem, is another way of thinking about this question. So what you're doing is that you're taking CP, you're taking a congruence class, which is like a big arithmetic progression. And so what Ben and I were doing is that we were spending a lot of effort to make all these numbers prime. But actually, for the purposes of the sieving, you don't need to make all these numbers prime in order to catch a lot of primes. You just need to have many of these numbers prime. And James, from his work on small Gasparian primes, had already found a way to produce lots and lots of tuples like this, where not everybody is prime, but maybe say 10 of these guys are prime. Okay, so he could find many patterns where large numbers of these numbers are prime, but not all of them. And this, so basically, if you just call this n and you call this h1 and h2 and so forth, it's exactly the same problem. The problem of catching lots of primes inside a congruence class is a special case of finding a sieve such that n plus h1, n plus h2, n plus h3, these all have a high chance of being prime. So rather unexpectedly, the same basic method which underlies the recent progress on small Gasparian primes has now been used to also create large Gasparian primes. So yeah, that is a very nice symmetry. Yeah, so we're still seeing what we can do further with these methods. Although I think for the purpose of small gaps and large gaps, we've pretty much reached the limit of what we can do with these ideas. But there are other problems in number theory which hopefully we can do something about. Okay, thank you very much.